This video is going to focus on electrophilic aromatic substitution using benzene rings that already have a substituent on them. All right, so we're going to divide our substituents into two general classes here. Activating substituents or electron donating groups. Okay, and when you put an electron donating group on a benzene ring, you get a compound that's more reactive than benzene in electrophilic aromatic substitution. So that's merely what activated means. It means you make the compound more reactive than benzene itself. Okay, so here are some examples of electron donating groups. We're going to classify them as being really strongly electron donating. These would include alcohols, amines, moderate, this would include ethers and amides, and weakly electron donating groups. The most common case of this is alkyl groups. Okay, this is not a comprehensive list of all things that you could put on benzene rings. These are just merely the most common things that you would see. All right. When we have an electron withdrawing group, abbreviated EWG like this, and we place it on a benzene ring, we end up with a benzene ring that is less reactive than benzene itself in electrophilic aromatic substitution. And we often refer to electron withdrawing groups as being deactivating. Okay, so we're going to call these deactivating. Okay, and activating groups. Okay, all right. Okay, so examples of strongly electron withdrawing groups include ammonium salts, nitro groups, and cyanides. Most specifically, nitro group is the strongest electron withdrawing group that we commonly encounter. Moderate electron withdrawing groups include anything with a C double bond O, be it an ester, a carboxylic acid, a ketone, or an aldehyde or an amide. Okay, CF3 is a moderate electron withdrawing group, and the sulfonic acids that we get from sulfonating benzene rings also tend to deactivate the ring as well. Weakly electron withdrawing groups, the most common one we'll see are the halogens, and all of the halogens show this property. They're weakly electron withdrawing groups. Even though fluorine is a lot more electronegative than iodine, their effect is really very similar. Okay, and all of these compounds are less reactive again than benzene in electrophilic aromatic substitution. Okay, now that we've classified benzene rings as either activated or deactivated, we need to add another substrate limitation on one of the reactions two of the reactions we previously encountered. That would be the Friedel-Crafts alkylation and the Friedel-Crafts acylation. These reactions cannot be performed on rings less activated than chlorobenzene. Okay, so we can have a weakly deactivated ring or an activated ring, but we can't have a strongly deactivated ring and still do the Friedel-Crafts reaction. All right, so let's look at a problem here. We're going to rank these compounds in terms of their relative degree of activation. Okay, we're going to outrank the most activated compound or the most reactive to any of the reactions previously discussed in this chapter as number 1. The least reactive is number 6, and number 2 through 5 were appropriate. And I'm going to add that a couple of these are kind of fuzzy, but on an exam I would probably not use 6 of these. I would use fewer, and they would all have very clear-cut answers. All right, so let's look at the array of substituents that we have on these groups, or on these benzene rings. There's 2 electron donating groups there. This is definitely going to be activated. Okay, so let's add that word here to express this, that this is an activated ring. Okay, All right, here we have one electron donating and two electron withdrawing groups. We're going to refer to this one as being deactivated because the electron withdrawing groups outnumber the electron donating groups. All right, so when we move the nitrile one further away, we now have this sp3 carbon right there interrupting the conjugation between the carbon-nitrogen triple bond and the benzene ring relative to the compound to its left. So here we're going to have one moderate electron donating group, a weakly electron donating group, and a strongly electron donating group. It's hard to classify this as being activated or deactivated because we don't know the relative strengths of all of these groups. All right, this one has a weak electron donating group. We're going to refer to this one as being an activated one. Okay, and the last one here is actually, we have three strong electron withdrawing groups and one weakly electron withdrawing group of fluorine. And, actually two of them are moderate, but really it doesn't really matter here because we're going to see that this one is going to overwhelmingly be number 6, and this ring here we're going to refer to as being a deactivated ring system. Actually quite deactivated. All right, so we're going to rank benzene somewhere in the middle. We're going to rank the activated rings ahead of the ahead of benzene, and the deactivated ones behind benzene. All right, so we're going to take this one right here as being our number 1 because it's the only one that's got nothing on it but activators and more than one activator. We're going to call this one number 2 because it's moderately activated by the weakly electron donating group. Benzene relative to toluene. Toluene is more reactive than benzene, but so we're going to do benzene next. All right, we're going to do this one number 4 mainly because this is a strongly deactivating group, and this these are weaker, but this is where our ambiguity is 3 versus 4. It's not clear whether benzene would be ahead of this one or behind this one. Okay, definitely this one here is not as activated as the one on the far right, so we're going to put this one, or not as deactivated as the one on the far right, so we're going to put this one as number 5. And finally, the one that's just chock full of deactivating substituents as number 6. All right. And again, if on an exam, we would design the exam so that it's very clear what ranks where. You would not have any ambiguities like you do in 3 versus 4 here. Okay. Now, we've looked at how these substituents affect their relative reactivity. There's another consideration when you have a benzene ring, and this concerns where does the new group go when you perform an electrophilic aromatic substitution on a benzene ring that already has a group on it. Okay? We can really classify our substituents into 3 general classes here. All electron donating groups are ortho-para-directors. All electron withdrawing groups except halogens are meta-directors, and halogens are ortho-para-directors. Okay, all right, so here's some examples here. If we look at, the compound here, this, of course, is an electron donating group, and we're going to see that when it undergoes an electrophilic aromatic substitution using chlorine, iron tribromide as the example here, we get a mixture of the ortho and the para products. Usually you get more para than you do ortho due to steric reasons. Okay, and this next one, this nitro group is strongly electron withdrawing. Okay, and when we do an electrophilic aromatic substitution here, we're using sulfonation as the example here, we're going to get exclusively the meta product. Okay, so we're going to get meta-nitrobenzene sulfonic acid. All right, and in this last one, I'll go ahead and circle it anyway, but it's very obviously a halogen. Okay, so we're going to find a ring that's less reactive than benzene, but when the substituent adds to the benzene ring, it's going to become an ortho-para director. Okay, so bromobenzene, when you try to do a Friedel-Crafts acylation on it, you get a mixture of the ortho product and the para product, and probably more of the para product than the ortho product. Okay, all right. And this, remember, is about the minimum reactivity you can have for a successful Friedel-Crafts reaction. It doesn't, any stronger electron withdrawing group than this bromine here, and our reaction would not proceed. Okay, so let's see if we can answer this question. Why are electron donating groups ortho-para directors? Again, if you're given this question on the exam, and like I told you before, just write the word resonance. This is a case where you'd get it right. Okay, it has to do with resonance. All right, so what we're going to do here is we're going to consider attack from the each of the three directions: ortho, meta, and para. All right, so in this first example here, we're going to consider attack at this carbon right here. Remember, this carbon has a hydrogen on it. Don't let those bond line diagrams and their missing hydrogens lead you astray. All right, so the attack here is going to put the partial positive right beside the OMe group. Okay, and this, remember, is an allylic carbocation, so we can write a variety of resonance forms. Okay, we have resonance form here and another allylic type resonance form here. So what we see is relative to where the bromine is, there's the localization of the positive charge over the ortho and para positions relative to where the bromine is, or relative to this asterisk carbon here. All right, there's an additional resonance form, however, that requires noting. All right, we've said that this is an electron donating group. That means it stabilizes electron deficient intermediates like carbocations. All right, so oxygen's electronegative. You may wonder how it does that. Well, it does that by resonance. The lone pair of electrons is going to donate to form this carbon-oxygen double bond, and we refer to this resonance structure not as a carbocation, but as an oxonium ion. Okay? All right, and it's really this resonance structure right here that's accounting for the ortho para orientation. We're going to see that para also, we can write the same resonance structure. All right, when we attack the meta position, and here we're going to hypothetically be considering the attack at this carbon right here. What happens here is that we get our initial carbocation, and it's delocalized again at ortho-para relative to where this asterisk is. Okay, there, and there. But notice that when you write these last two resonance structures, you kind of just bypass the OMe group. You never have any resonance form where the positive charge is directly beside the OMe group, or directly beside the OMe group, directly beside the electron donating group. And because we never put the positive charge really close to the electron donating group when we attack the meta position, meta attack is not as favorable for these activated ring systems. All right, finally, let's look at para. Okay, so we're going to consider attack at the para position right here. And note that the second intermediate that we draw, okay, initially we get this carbocation here, but we start drawing allylic resonance structures. And the second one that we draw has the positive charge directly beside the OMe group, or directly beside the electron donating group. Okay? And because of that, Okay, we have this resonance stabilized carbocation, and say that attack in the para position is also favorable. All right, we have 4 different resonance structures for the intermediate carbocation, and we're going to say that this is actually the one that's the most important. And that's because this one, all carbons and oxygens have octets in this resonance form right here. So this makes is another reason why we like to show the oxonium ion resonance form. All of these have a carbon that doesn't have an octet. A carbocation does not have an octet. There's only 6 electrons buzzing around this carbon right here, as there is here. And here there's more because we can write that resonance form right there. Okay, if we go back and compare the resonance forms here, this one is also the most important. Okay, because again, this gives us an octet in all of the oxygens and carbons. All right, or all the carbons rather. Oxygens have octets everywhere. Okay. All right, so now we're going to look at why our electron withdrawing groups meta-directors, and it's exactly for the opposite reason. All right, so we're going to consider the meta-attack first, and we're going to consider attacking the bromine here in this bromination reaction at this carbon right here. Okay, when we attack this, we generate initially the carbocation. Okay, and we start drawing the allylic resonance forms. And notice how we, relative to this position that I've asterisked, we see the positive charge delocalized over to the ortho-para positions relative to this position right here. And, okay, all right, so that positive charge is ortho to that bromine. That's what I mean when I say relative to this, okay? All right, but really, it's meta relative to the nitro group. Okay, all right, so look here. The electron, the nitro group, okay, yeah, we'll just illustrate that with the next one, sorry. But the key thing here is that electron withdrawing groups are electron hogs. They want electron density, and when you put a carbocation directly beside something that's withdrawing electrons, that's really bad because the carbocation doesn't have any electrons to give. All right, let's consider para attack, and we're not really going to consider ortho attack anymore because we've seen that we write similar, or that we delocalize the positive charge in the same places for ortho and para attack. So let's just consider para attack. We're going to consider attack right here in this bottom case. All right, so attack is occurring. Positive charge is initially here. We start drawing the allylic resonance forms, and right away we see one that we don't like, right? We see the positive charge right beside of the nitro group. Strongly electron withdrawing. It's pulling electron density away. It's pulling electron density away from something that's already very electron deficient, and that's bad. All right, so we can sort of see that a little better here when we draw a nitro group out into its Kekulé structure here. And what you see here is that you have 2 positive charges, 2 full formal positive charges right beside each other, and that's not good. Okay, all right, so for that reason, we do not want to attack the para position or the ortho position, because in the intermediate carbocation, there's a lot of positive charge character directly at the electron withdrawing group, and that's a bad situation. Okay, finally, let's look at halogens. All right, so let's consider para attack. What's good about attacking a halogen in the para position? Okay, so we're going to consider attack at the para carbon right here in this bromination reaction. All right, so we're going to initially produce the positive charge here. We're going to start drawing the allylic resonance forms. And let's focus on this one right here. Let's see, we known for a long time that chlorine is electronegative. Okay, so therefore, that's a bad situation, right? Because we are destabilizing the positive charge. But chlorine also has lone pairs. Okay, and we can write a resonance structure, the one that you see down here at the bottom. It now has an octet. It's not a carbocation anymore. It's, I guess, a chlorinium ion or something like that. All right, so what we can say here is that halogen, and all the halogens have this property. We say they're they're inductively electron withdrawing because they're electronegative, but they can stabilize carbocations via resonance. Okay? All right. So this inductive electron withdrawing accounts for why these are deactivated ring systems. Okay? When electrophile approaches the neutral benzene ring, there's no need to stabilize any sort of positive charge or anything, so the inductive effect is more important than the starting material. But once you form the carbocation, you can stabilize it by resonance, and that's why we see this orthopara orientation. Okay, so you can only get the positive charge right beside the halogen when you attack the para or the ortho position. All right, and finally in this section, we're going to look at orientation and multiply substituted benzene rings, or benzene rings that have more than one substituent on them. Okay, there are three guiding principles here. Principle number one, and this is the most important one, the strongest electron donating group dictates the orientation. The overwhelming concern is that you want to perform the electrophilic aromatic substitution ortho or para to the strongest electron donating group. If there are two or more rings, the most activated ring will preferentially undergo electrophilic aromatic substitution. And then finally, we're going to say substitution between two metagroups is sterically disfavored. So if you've got another site available that is sterically a little better, you'll probably see substitution there. But if this is the only place you can substitute, it would happen at that place. Okay, all right. So let's look at some scenarios. Here, relatively easy to predict in these cases because both of the groups want the same thing. All right, the methoxy wants it to go ortho-para. It can't go para because there's something already here, the carboxylic acid group. Okay, so we don't see attack at the para position. We see attack at the ortho position, but the carboxylic acid also wants attack to go here because it's a meta-director, and it wants it to go here as well. So everybody wants the sulfonation to occur ortho to OMe, and that's exactly what you see. We're going to call the OMe the boss group, the one that's going to control it because it's the strongest electron donating group. It's actually the only electron donating group in this case. But even though the COH doesn't have a voice in this, it still agrees that the substitution should occur at exactly the same place. All right, here we have two electron donating groups, and they're in the meta arrangement. And this is also a situation where both groups are working together. All right, so the OMEs are activating the ortho and para positions relative to OMe. So this position is activated, this position is activated, this position is activated. But this position right here is between two meta groups, so we're not going to see attack here. Okay, and well, we see that there's also some symmetry in this molecule, so attacking this carbon is equivalent to attacking that carbon right there. All right, so the Friedel-Crafts acylation is going to occur there. Okay, and this is the product that we would get. We get the product from attack here also, but it's equivalent to attack here. It would just be the same product, just oriented at a 120-degree angle. All right. All right, so here's a problem here. We're going to predict the product of each reaction. Okay. All right, so let's look at the first one here. What's the strongest electron donor? Is it OMe? Is it methyl? Or is it chlorine? Well, we could probably see that the the OH is our controlling group. Okay. All right, so we'll just say that this is our, we'll call this one our boss group here. And this tells us where to put it. It says the substitution could go here, here, not here, but it would like to go para, but something's already there, so it's not going to occur here. So that's our product. Okay, let's look at the one to its right. All right, so we have two rings here. What we can probably see is that this ring here is deactivated. This ring here is activated. All right, so we're going to do our substitution in this ring here. This is a methyl group. It's competing with the other benzene ring, but the methyl group is actually a stronger donating group than a benzene ring. Okay, and we're going to see that attack is going to occur in the activated ring, ortho or para to the methyl group. It's not going to occur para because there's something already here, and the product is the one that you see right there. Okay, and this one on the bottom left, what we're going to see here is that we have two groups here. We have the oxygen group and a carbon group, and we're going to identify this group as our boss because an ether is a moderately electron donating group and an alkyl group is a weakly electron donating group. So moderate is a better or stronger electron donor than weak. Okay, so this Friedel-Crafts acylation, okay, is going to occur ortho or para to the oxygen. And we would expect a mixture of these two products right here, probably a little bit more of the para product because generally sterically it's a little more favored usually, but we would see a sizable amount of the ortho product as well. In this last one, we also have two rings, and we note here that we have this ring is deactivated because the only substituent on this ring is a carbonyl group, which is an electron withdrawing group. Okay, on this ring, we have three electron donating groups, this amide group, an alkyl group here, and another alkyl group here. Well, the amide is a moderate electron donating group. These are weakly electron donating group, alkyl groups, and so when we perform this Friedel-Crafts alkylation, we're going to expect it to occur ortho-para to the nitrogen, and right here is the only ortho-para position that has a hydrogen that we can substitute. This one is between two meta groups, so it's going to be less likely, and this ortho position here already has something on it. Okay? All right, so the product that we have there is going to, or the product depicted there is going to be the product of the reaction. All right, so I think this is where we're going to stop with this video. In the next one, we're going to look at how to plan a synthesis when you need a specific orientation. Okay, so that will be the subject of the next video.